Hello and welcome to another video. In this video we're going to be working on find if path exists in a grid. And in the problem you basically have a graph with an undirected graph, meaning for every edge you can traverse in both directions. So if there's an edge here you can go this way or you can go the other way. And so they tell you where the edges are, and basically you're given a source and a destination, and you want to return true or false if you can get from the source to the destination. So here source is 0, destination is 2, so there's a path. There's a bunch of paths. You can go this way, you can go this way, and so on. And then second example, source is 0, destination is 5, so you can't get there, so you return false. And that's basically the idea. So build a graph. It's basically like build a graph and do a traversal. So there's 3 ways you can do this. 2 are kind of standard and 1's more unique. So one is a depth first search, just a graph depth first search, like build a graph and do a depth first search. Second, breadth first search. And third is a union find. So I'll briefly talk about it, but I'm not going to implement it because it's an easy problem. So I think this is beyond the scope of an easy problem. But basically what union find does is it connects, whenever there's an edge, it will connect all of your components that are connected by the edge. So for this, all of these nodes will be connected. So if I can call a function called is connected, this node and this node, it will return true. And then it's pretty easy. So you make a union find and then you just put in the source. You just call is connected on these 2 nodes and it will tell you no because they're in different components. So this is one component, this is a second component, and so on. And in this is only one component, and so on. So you can look up union find if you want to. We'll just do a breadth first search. And I usually do breadth first search for most graphs. So I either go pretty much for almost all graph problems, I either use breadth first search if it's a shortest path where edges don't have a weight, or I use a heap if it's a shortest path where edges do have a weight, or union find. These are the main 3 I use for a graph. I almost never use a depth first search. So in this case, actually, you want to recognize that you can actually do a breadth first search, and typically a breadth first search is with a queue. Because let's say I want the shortest path from 0 to 2. I would use a queue, but just to see if nodes are connected, you don't need the shortest path. So you can just do a queue, a stack, any kind of array, any kind of traversal. We'll use a queue just kind of to show good practice of it, and I'll give you kind of a template of how to do a breadth first search, but you can use anything else, like a queue, a stack, and a list, and so on. But that's kind of the idea. So first we're going to build a graph, so I'll show you how to build a graph, which is necessary for all graph problems, and then I'll show you how to do a traversal. And to build a graph, the idea for a graph is let's say for this graph, for example, basically the format for a graph is you want the key to be the node, so for example node 0, and you want the value to either be a list or a set of nodes it's connected to. So for 0 it'll be 1, 2, for 1 it'll be just 0, for 2 it'll be just 0, for 3, it'll be 4, 5. For 4, it'll be 3, 5. And for 5, it will be 3, 4. So this is kind of the format we want for a graph, and then I'll show you how to do a traversal and all that stuff. A standard BFS that you can use for shortest path of unweighted edges. And how to have a visited set and all the format and all that stuff. So let's get into the code. So first we'll build a graph. So remember, our graph needs to be the key needs to be an integer, and the value needs to be either a list of integers or a set. So we'll use a list of integers in this case. So we'll say map integer, and then list integer, and we'll call this graph equals new map. Okay. And then we are going to go through all of our edges. And so for every edge, let's say there's an edge like this, what we need to do is we need to put 1 in the list of integers for 0, and we need to put 0 in the list of integers for 1. So we need to add this and this. So for every edge, we need to add 2 things to our graph. So let's do that. So we can say for int array edge and edges. So first what we want to do is we want to make sure that I guess first we want to get the 2 values. So we can say int x equals edge 0, int y equals edge 1. Then we want to check if both these keys exist in the graph. If not, we'll make a new list. So we can say graph And so there's one thing I learned recently today. You can use put if absent. And so what this will do is it'll give a value to a key if the key isn't in our hash map. So that's kind of useful. So if X does not exist, we want to make a new list. So this is new array list. And if we need to do the same thing for Y. So but if absent, Y, new array list. So essentially just if this key isn't in here, put it in here and give its value in array list. Now that we know these keys are in there for certain, we can put X in the list for Y and Y in the list for X. So let's do that. So graph dot get, and this is going to be X. So this will give us the list of children for X, and then we can just add Y to it, and graph get Y, add X. So now our graph is done. Now the next part is we need to make a BFS and a visited set. So BFS, we'll just use a queue. I think probably in Java the best thing is just stick with an array deck, and you can use that for queue and stack. It's like a double-ended queue, so you can use it for both. So we can say deck, I believe, and this is going to be integer BFS equals new array deck. So yeah, double-ended queue. Same thing as a deck in Python. So you can technically use a deck in Python for a stack and a queue. It does both. But you can also use an array in languages for a stack, which is what people do. So yeah, you could use like a list for a stack instead as one. I think the actual stack data structure is like not used super often in Java. People just use the double-ended queue. So what we want to do is we want to put our source node in here. So BFS. And so this is a little weird. So for this double-ended queue, add pushes to the back, and push actually pushes to the front, which is kind of weird because in most languages push pushes to the back. So we can add it to the back like in a normal queue. We can add, whoops, what am I doing? BFS add, we want to add our source node. And we want to make a visited set. So we can say set integer visited hash set. And we want to add our source, and I'll briefly explain why we can do this here. Why like for a breadth first search specifically, where edges are 0 weight, we can do this format instead of like waiting till we pop, because this will be more performant. So visited add, I think, and then this will be source as well. Add or insert or something. Yeah. Okay. So the idea is when we have a queue, if we have an element in here already that we're traversing to, like let's say we just have a queue of like 0, 1, 0, 1, 2, 3, and so on. So because in a queue things are first in, first out, if a 2's in here already, if I add a 2 in again, this 2 will come out first no matter what, right? So if something is in the queue and you put it in again, because the order is maintained, the one in there first will come out first. So if something's in there already, you never have to put it in. So you can mark things as visited, right, when you put them into the queue. And that makes sense. But for something like a heap, you can't do this, because for a heap, you might put something in at the end, but it actually might come out first because it has like the least weight. So for the weighted things, you want to mark things as visited only when you pop. But for a BFS, you can mark it as visited as soon as you insert it into the BFS. Because the order is preserved. So that's why we can mark these things as visited before we even pop them and like actually visit them and pop them out of our BFS. Okay, so now the standard BFS is basically we say while our BFS has items, so is empty. So while it's not empty, we can pop items from the left, right? And so so basically this will guarantee that if we start at a node and all the wedges, let's say all the edges have like a weight 1, we're going to get to our end the fastest way possible using a BFS. But if all the edges have actual weights, like if this is weight 5, this is weight 4, and so on, then we'd want to use something else. But for BFS, it's guaranteed that, you know, if everything is weighed the same, or if you have like a matrix or something, you're going to get to your result the fastest way possible. So basically we want to do a node, so int node equals BFS, and then we want to pop from the front, so this is going to be pull first. So we get our node, and then if our node equals destination, then we can just return true because we made it from our source to our destination. So remember, we don't have to check if the node's visited already because everything that we pop from here will already have been visited. We mark things as visited right when we put them into the queue. So then we have to check if the node actually exists in the graph, right? Because like, let's say our source is like 3 and let's say it's like something like this. So we're at 3, we're trying to get to 5. We're gonna pop this. This doesn't actually exist in the graph because there's no edges. And so we don't need to like traverse this node's children. So we're gonna check if graph contains key. So this is like if this key is in here, node. So if this node isn't in the graph, we'll just continue because there's nothing to traverse from here. We're done with this node anyway. Now we have to traverse through all of the children of the node. So like if we popped 0, we have to put all of these nodes into the queue. But we only put in the nodes that we haven't visited yet, and we'll mark them visited. So here we can say for int child. And now that we know that the graph has a node for sure, we don't have to check if it does. So in child in graph.get node, if visited contains. So if we haven't visited this child yet, if it's not in our queue, then we're going to mark it visited. And we're going to put it into our queue. So add child. And if we go through this whole BFS and we weren't able to make it to our destination, that means we couldn't get there, so we just return false. So this is the basic template for a BFS. So just to recap, build a graph, make a BFS in the visited set while the BFS isn't empty, keep popping nodes. If the node is your destination, return true. If the node isn't in your graph, you can't traverse anywhere. And for all the children of the node, check that they haven't been visited. If they have been, skip it. And if they haven't, add it to visited, add it to the BFS. And this is where you want to mark things as visited to ensure that you only add nodes to your queue one time. Otherwise, what can happen is you might actually, like let's say we didn't do that. Like let's say what can basically happen is you can go to a node, you can pop like this node, and maybe this node has, like siblings, these 3 siblings as well. And then you're going to put them in again. So it's going to be like less efficient. And even though you put them in again, these 3 will come up first. So these 3 are completely useless. So that's why. Okay. Yeah. And then we're done. So we can just do this. Yeah. And pretty good. And the time complexity for a BFS, if we look at our graph, so essentially we're going to start at a node, and worst case scenario, we're going to visit every node once, so that's going to be O of n. Yeah. But also, to build the graph, we have to actually go through all the edges, right? So it's going to be O of n plus e. So it's typically written like this, vertices plus edges, because to build the graph, we have to traverse every edge. And then to do the BFS, we have to traverse every node. So it's like this, space, same thing. Because in the graph, worst case, like for every edge, we have to put it in the graph. And then also in the BFS, we might have to traverse every node. So it's going to be, yeah, it's typically like this. For a union find, it will be less. So it will be O of v plus e, because you do have to traverse every edge. But for the space, it's only O of v. You don't store edges in union find, you just connect things that are connected by an edge. So union find is more space efficient than a BFS, but typically you can't just use union find, and typically you're not asked to see like, can I start from here and go to here? Like that's, I mean, this is kind of like an easy medium maybe it's a little hard for, like, I don't think any problem's like easy for a graph, but yeah, you're almost never asked like, given A, can I go to B? It's more like, given A, what's the shortest path to B? And honestly, even something like that is kind of easy, so they usually like, make it significantly harder than that. But this is what you can use for the graph. So yeah, it's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And I'll see you next one. Thanks for watching.